Let us have a look at the course contents. The first topic which we will deal with is three-dimensional stress analysis. Now, while dealing with the design or redesign problems, the design engineer knows that the design must function according to prescribed requirements, as well as the design must have an acceptable level of structural integrity. Now, the stress analysis is that part of the design process which ensures that each element of a given system will not fail to meet the structural requirements of the design throughout its operation. Therefore, for the safety and reliable operation of any system, an accurate and efficient stress analysis procedure must be carried out. So in this particular chapter, we will study how to carry out the three-dimensional stress analysis, which means that we have to determine the stresses on all the faces of an arbitrary three-dimensional element as shown in the diagram. So further, we will try to look at the stresses on an arbitrary plane, and since an arbitrary plane may have the normal stresses as well as the shear stresses on it, so we tend to go towards the principal plane and determine what are the principal stresses and what are the strain invariants on those planes. So these are some of the important topics of three-dimensional stress analysis. Further, we go for so this shows that stress on any arbitrary inclined plane which is inclined at an angle of theta degree to the original Cartesian axis. Further, we can show the graphical version of all these transformation that is given by Moore's three-dimensional stress circle. And since we have to deal with Cartesian coordinates, and we have to deal with components like curved bars, like crane hooks, so we have to deal with the cylindrical coordinate as well. So therefore, we will derive a differential equation of equilibrium for Cartesian coordinates as well as the cylindrical coordinates. Further, after stresses, it is also very important to determine the strain in the three-dimensional plane. So we go with three-dimensional strain analysis. What are various rectangular strain components, and obviously strain components at a principal plane, and the strain invariants. It is very important to see the relationship between stress, strain, and how the mechanics of a deformable bodies are dependent on these parameters. So I hope we will be discussing in detail in this chapter. At last, we will discuss with the compatibility conditions for the strain components, right? Our next chapter will be on stress strain relationships. So once we have developed the stress and we have defined what are strains, we will try to look at the relationship among the two. And in general, we have been dealing with these relationships are linear in nature. Okay, so we can go with certain assumptions, like in a general elastic body there are about 81 constants, and for an isotropic material there are 2 constants. So I think we will have in detailed discussion how we are coming from a 81 constant to 2 constant criteria. Okay, so we will discuss a generalized Hooke's law for that. Our next content will be the energy methods. In these methods, we will try to understand certain principles like principle of superposition, and we will try to visualize the physical system in terms of the energies. So we will try to find out what is the elastic energy stored when the structure is subjected to the bending loads, subjected to compressive forces, subjected to torsion, subjected to any axial tensile or compressive forces. So in that way we could actually determine how much energy is being stored, and we can use this principle of minimization or the Castigliano's method or the Maxwell-Betty's theorem to actually solve the problem. So we will determine what are the strain energy expressions. We may use a Fichte's load method. So the advantage of energy methods is that it can be easily applied to statically indeterminate problems as well. So we can solve statically determinate problems as well as statically indeterminate problems. Our next topic comes is unsymmetrical bending. In unsymmetrical bending, our section may not be symmetrical with respect to both the axes. In symmetrical bending, what we have done in our elementary courses, where the bending equation we write as sigma by y is equal to m by I. So that particular equation is valid for symmetrical bending. So, and for that the assumption is your beam section must be symmetrical with respect to at least one axis. But in case your beam section is such as like L section, okay, so the bending will not be symmetrical, and that a particular equation we cannot use. Moreover, we also assume that the loads are being applied through the perpendicular to the axis. In case the loads are not being applied perpendicular, so that also will produce a unsymmetrical bending. So these are certain realistic assumptions which are needed to be considered. So unsymmetrical bending, we will consider these assumptions and will definitely go for the more realistic and efficient design. And the next chapter we will deal with the curved flexural members, in which the curved members like crane hook, like your lock, so these members will be analyzed, and obviously we require certain equations now in polar or cylindrical coordinates. So we will have one Winkler back formula for this, and we will try to determine what are the stresses in the curved beams in the inner edge or the outer edge. Here also we will have to take up certain sections of a curved beam. That section may be circular or rectangular or maybe a trapezoidal section. Okay, so next we have thick and thin cylinders. We generally encounter many applications which involve the cylindrical components such as thin cylinder and thick cylinders, mainly used in the pressure vessel industry, as well as we have the rotating disc. So in this particular chapter we will deal with thick cylinders and rotating disc. It is very important to determine the stresses within the thick cylinder, which may be the tangential stress, longitudinal stress, or the axial stresses. The Lami's theory describes these stresses quite precisely, and we will be discussing the Lami's theories in detail. Further, we will reduce it to thin rotating rings and stresses in the rotating disc and cylinders. And the second last topic we have is helical spring, where we find the deformation of how the deformation of a helical spring takes place. And the last chapter we deal with the theory of elastic failure. So it is very important to see, once we evaluate the stresses within a component, whether it is a beam component or a cylindrical component or a curved beam component or a spring. So it is very important to see whether it is in the safe zone or it is failing because of the exceeding the upper limits of stresses or deformations. So therefore we have various theories of failure for brittle and ductile materials, and we will mainly focus on significance and application of these theories of failure in detail. So this will be all about we will be dealing in our course. So thank you very much for paying the attention.